Hi, grade 12s. In this particular video, we're going to be looking at integrals involving natural logarithms, and the natural logarithm, hopefully remember, is the ln of x. So that's the logarithm with the base number e. Now, in order to do these integrals involving natural logarithms, we always have to look at the derivative first, because if you recall, integrals are the reverse operation of differentiation. Okay, so on your formula sheet over here, hopefully you guys can see that if I integrate ln of x, if I differentiate ln of x, I get 1 over x. So the derivative of ln of x is 1 over x. So logically speaking then, if I reverse the process, then the integral of 1 over x has got to be ln x. So let's look at that. So if the function is ln of x, the derivative is 1 over x, then the integral of 1 over x is ln of x. But there's one small little thing you have to please be aware of, and unfortunately it's not on your formula sheet, so this is something you have to memorize. And that one little thing is this. Whenever you integrate 1 over x, I agree that it's equal to the ln of x, but you have to put absolute value brackets around that x. And that simply has to do with the fact that we cannot allow a negative value to go into a logarithm. I don't know if you guys recall, but if I go and I type in, for instance, the ln of -2, it tells me it's a math error. And that is why it's so important that when you integrate, you have to remember that in the original function, x could potentially have been positive or negative. But over here, x must always be positive. And that's why we have to put those absolute value brackets in. You'll see I'm going to hammer on it in every single one of the examples. And then obviously, please remember your plus c. So that, like I said, does not appear, unfortunately, on the formula sheet. So what you might have to do is when you get your information sheet before you start writing, just please remember to put those absolute value brackets there, so that when you integrate, you use the absolute value brackets. Okay. Now, if we look at these examples, in other words, if I didn't just differentiate the ln of x, if I differentiated the ln of fx, hopefully you guys will recall, this is a chain rule example. So according to the chain rule, over here, what I would have had to do is I'd first have to go and differentiate ln. So differentiating ln would mean 1 over whatever's inside the bracket there, so fx. But be careful, because of the chain rule, I then have to go and differentiate what's inside that bracket. So then I have to multiply by the derivative of that fx, which then results, if I clean it up, in the derivative of fx over fx. But again, with integration, please remember integration is the reverse of differentiation. So that means if I asked you what was the integral of the derivative of a function over the actual function, then you guys should be able to work it backwards and realize it's going to be equal to the ln, and careful, absolute value of fx plus c. And this is why whenever we integrate fractions, so if I have a fraction, specifically, remember it could be a constant over linear, but it could, for instance, be a linear over quadratic, it could be a quadratic over cubic, because remember, the numerator must be the derivative of the denominator. So if I have a fraction where the numerator's degree is 1 less than the denominator's degree, then the chances are very, very, very good that this is going to be one of these ln of fx integrations. Okay, so let's look at some examples. This is example 1 on page 86. So you'll note at the moment it doesn't exactly look the way we want it to look, because we want to know that the integral of 1 over x is ln of x. But that 4, if you think about it, is going to be a constant. Now careful, it's not really 4, it's 1 over 4. So take out the constant 1 over 4, put it in front of that integral, and then I'm back to exactly what I did in that previous one, which says that the integral of 1 over x is the ln of the absolute value of x. So I can say it's 1 over 4 ln of the value of x plus c. Pretty simple and straightforward with these constants. Next one. Now this one, it's not really a constant that we can take out like the previous one. But you'll notice that if you did try and integrate it the normal way, and when I say the normal way, I'll just compare it over here, which is take that 2x minus 9 and make it 2x minus 9 to the power of negative 1 dx. Then if I tried to use the normal integral technique, I would have first gone and said, take the exponent and add 1 to it. So minus 1 plus 1 is 0. But then remember, you have to divide by that new exponent, and you can't divide by 0. So if you tried to do this the normal way, you would have realized the normal way doesn't work because I can't divide by 0. So it's a fraction with a constant over linear. I just have to make sure that the derivative of the denominator appears in my numerator. So that's what I'm going to do to fix this one up. So my denominator is 2x minus 9 dx. The derivative of the denominator is going to be 2. So I just have to make sure there's a 2 over there. Then now the numerator is in fact going to be the derivative of the denominator. But because I put a 2 over there, I have to fix it by putting a half over there. So a half times 2 is 1. So I didn't change the expression. Now I can go and I can say this is then going to be a half. And now this is where you have to be careful. The answer is always going to be the ln of the denominator. So going back to this, if you integrate the derivative of a function over a function, the answer is always going to be the ln of the denominator. So this is back to that reverse chain rule again, where remember, whatever the derivative of fx was, we kind of throw it away. It goes back into the Russian doll, it disappears. So that's why I'm going to have half ln absolute value only of the denominator plus c. So there, this should be pretty easy and straightforward. It becomes slightly more complicated when I involve the partial fractions. You'll see just now how partial fractions apply to these ones. Here we have another one. So currently, I'm looking again at that denominator, 3x minus 2. I want 3 to be over here. That's what I want, because the derivative of 3x minus 2 is 3. Currently, it's not 3, it's 6. But I can fix that. If I put a 2 out there, then 2 times 3 is 6. So I haven't changed the expression, and now I have the derivative of the denominator. So this is going to be 2 ln of the absolute value only of the denominator, 3x minus 2 plus c. They do get fairly straightforward once you've done a couple of them, but like I said, you have to spot them. You have to realize that the technique of using the negative exponent and then adding 1 to the negative exponent doesn't work because your exponent becomes 0. So the moment you get that situation, you should then go and ask yourself, maybe it's one of these ln ones. Okay, let's take a look at the next one. The next one then says the integral of cot x dx. Now this one, when you just look at it, does not look like this natural logarithm one. But we learned when we did the trig integration that we're going to have to use identities, because if I look at my table and I read it from right to left, you'll notice there's no standard integral for cot. There's no cot of x on this side. So there's no standard integral. So then I can go back to my identities and I can say cot is equal to cos of x over sine of x. Hopefully you guys will recall this, because cot of x is the reciprocal of tan x. So if tan x is sine x over cos x, then cot x is the reciprocal, in other words, cos x over sine x. Now, if you look at this, you'll see it's a fraction. Not only is it a fraction, but the derivative of sine x is cos x. So that is the derivative of this, which means this is simply the ln of the absolute value of sine x. So because cos x is the derivative of sine x, again, the moment the derivative appears in the numerator, that disappears, and it's going to be the ln of the denominator plus c. And remember those absolute value brackets. So this one then should also be fairly straightforward. I change tan of x into sine of x over cos of x. And again, I notice that the derivative of cos x, careful, is not exactly sine x. The derivative of cos x is supposed to be minus sine x, but that's not an issue. I can fix that. I can make this minus, I can make this minus, and now minus sine x is the derivative of cos x, which means I can throw away the numerator and it's equal to the ln of the absolute value of the denominator, which is cos x, and then plus c. Remember the absolute value brackets. I know it's going to get annoying for me to say, but please, they do penalize you if you don't put them in there. Now, even something as complicated, that looks as complicated as this, you should be able to notice, again, it's a fraction. I look at the denominator and I ask, what is the derivative of that denominator? Well, the derivative of sine x is cos x. That's correct. The derivative of cos x is minus sine x, so even that is correct. So I don't even have to manipulate this one. I just know it's going to be ln of the absolute value of the denominator. So sine x plus cos x, absolute value brackets, plus c. So sometimes something that looks super complicated, the moment it's a fraction, just check whether the derivative of the denominator is in fact the numerator, and then it's just going to be the ln of the denominator every single time. So if we look at this one, again, it's a fraction. So I look at the denominator and I say the derivative of e to the power of x is e to the power of x. In case you've forgotten that, it's also on your formula sheet. The derivative of e to the power of x is e to the power of x. So I know that's right. Then, the derivative of e to the power of minus x, please remember, that's a chain rule. So that's going to be e to the power of minus x, but then you have to multiply by the derivative of that minus x, which is minus 1. So the derivative of e to the power of minus x is e to the power of minus x times negative 1, and there it is. So the numerator is already the derivative of the denominator. No manipulation required. So I can just say it's the ln of the absolute value of that denominator, e to the power of x, plus e to the power of minus x, absolute value brackets, plus c. Okay, not too bad. Now, the only place where these ones get tricky is in the following one. This one, you'll clearly see, you have x times x minus 5. So this is linear over quadratic. So the moment you get these fractions where you get linear over quadratic, if you go and you multiply this out, and if you take it up to the top, trust me, it's not going to work. Normally, though, what they do with this example like this is they do break it up, they scaffold it. They give you a clue saying to you, number one, break that up into partial fractions. So this is where the partial fractions comes in. Luckily, it's already factorized. And because it's already factorized, I know this is a type 1. See, linear factor, no recurrences. So I can say it's a over x plus b over x minus 5. Multiply by the LCM of the denominator, so I have 1 is a times x minus 5 plus b times x. Then I can use the cover-up method, because remember type 1, cover-up method works perfectly. I can cover this up by setting x equal to 5. So 1 is then equal to, this is going to be 0 obviously, so a times 0 is 0, plus 5x, sorry, b times 5, which means b is then equal to 1 over 5. And then I'm going to set x equal to 0 to cover this one up, which means 1 is then equal to 0 minus 5, so a times negative 5 plus bx, which is then 0. So that means a is then equal to minus 1 over 5. So I can then go and I can rewrite this one. And I can say it's therefore the integral of a over x, which is minus 1 over 5. So I'm going to write it like this. Minus 1 over 5x plus then b over x minus 5. And by the way, sorry, it's a little bit difficult to see like this. Hopefully this is better. So we said, remember, a is equal to minus 1 over 5. So that's minus 1 over 5x. So that's why I've written it's the integral of minus 1 over 5x. But hopefully you guys will remember that because of integrals being split by pluses and minuses, the moment integral is split by a plus and a minus, I can break this up into two separate integrals. So the integral of the full fraction is then going to be the integral of the partial fraction, but I can do it bit by bit. So the integral of the first fraction plus the integral of the second fraction, and that's what I'm going to do now. So it's the integral of the first fraction, which is that a, which is minus 1 over 5x, plus then the integral of the second fraction b, and we said b is positive 1 over 5, so that's going to be positive 1 over 5 times x minus 5. So just to remind you, I can go and say, because this can be written as this, I can break this integral up into the two parts, and I can say it's going to be equal to the integral of that, and whatever the a value is, plus the integral of that one, and there also whatever the b value is. So now it actually becomes pretty easy and straightforward. Here I can take out the minus 1 over 5 and say it's the integral of 1 over x dx. And there I can also take out the 1 over 5 and say it's the integral of 1 over x minus 5 dx. Now this one, if you look at it, is my straightforward integral of 1 over x. So that's going to be minus 1 over 5 ln of the absolute value of x plus 1 over 5. And again, this is a fraction, and the derivative of the denominator is 1, which is the numerator. So that's also ln of then the absolute value of that denominator plus c. So this is why we needed the partial fractions. We needed the partial fractions specifically in order to go and break it up, and so we can do the integration. Now they actually went, and last year in the IB 2019 exam they gave this example, and they scaffolded this one where they said, number 1, break that up into partial fractions, and then number 2, determine the integral. So if I do the partial fractions over here, step 1, partial fractions, always factorize. Now you'll see it's cubic, and it's not an easy cubic, so I'm again going to use my calculator to help me out. So I'm going to say it's 3x squared plus 11x minus 5 over. And I'm going to change that to equation mode, and I'm going to say cubic, so number 4. And I'm going to say my a value is 1, my b value is 3, careful, my c value is 0, because there's no x, and then my d value is minus 4. Now you'll see it gives you x1, which is equal to 1, which means the first bracket is x minus 1. Remember to change those signs. Then it gives you x2, and that second one is negative 2, which means the second bracket is x plus 2. Now, we're expecting to get a third bracket, but this was the tricky one. If I press equal, you'll see there's no third bracket. Now, the only way that there's no third bracket is if one of these two brackets repeats itself. Because cubics normally give me linear times quadratic, or it gives me linear times linear times linear. So if it only has linear, it means one of these two repeat, and that's why it doesn't say it again, because it only has those two factors, or I should rather say those two zeros. So this is the only tricky part, is now we have to determine which of those two brackets is going to be squared. But hopefully you guys should look back at this top and realize the only way we're going to get this by multiplying these two out is if this is squared. And it's quite simple. It has to do with that 4. If I square this one, I'm going to get 1 times 2, which doesn't give me the 4. But if I square this one, I'm going to get 4 times negative 1, which gives me negative 4. So if you do ever use the calculator to break this up into the 1, 2, 3 brackets, and you only end up getting 2, you're going to have to, by inspection, determine which one of them repeat. Okay, which one of them repeats. So this one then is a type 2. So it's going to be a over x minus 1 plus b over x plus 2 plus c over x plus 2 squared. There we go. So this is then the first step. What I then want you guys to do is completely on your own, and obviously in the notes I'll fix it up, But on your own, I want you guys to try, finish up this partial fraction, and once you finished up this partial fraction, use the partial fraction in order to do the integral of that. So I want you to try it completely on your own, and then in the notes you'll see what the solutions are, so you can then go and you can check your answers. Thank you very much for listening.